All right, welcome back to week two of the live interactive sessions of the course Fundamentals of Conduction and Radiation. In the previous week, we basically looked into a very introductory concept of the three modes of heat transfer, that is conduction, convection, and radiation. And we touched upon the basic, law of conduction heat transfer, that is the Fourier's law. We looked we saw what is the most generalized form of the Fourier's law. And then, under certain assumptions, for instance, that your thermal conductivity is constant, that is, it is not varying along either it's not varying along a particular direction or it is not varying along, you know, it's not varying along the space, and it is also not a function of temperature. And then we try to apply the Fourier law in one or two problems. And then subsequently, we also looked into a problem where your thermal conductivity, although it was not a function of space, it was a function of temperature. And consequently, we saw that the temperature distribution was not linear, which was otherwise the case when thermal conductivity was constant. So this is something that we had a look in the last week, and we ended by understanding the fundamental difference between convection, conduction, and advection. And as we saw that convection is a more generalized term which takes into account the bulk motion of the fluid, which we call it as advection, and it also takes into account the molecular diffusion that takes place due to the presence of the due to the motion of the molecular movement of the molecules, which precisely is known as diffusion, as I say. So you can say broadly that convection is the summation basically of crudely speaking, you can say that it's the combined effect of this bulk motion as well as the molecular diffusion, which we call it as conduction. So it's advection plus conduction, which gives us convection in general. And we also looked into we just touched upon the basic, form of heat transfer due to radiation. And we said that when we will be learning radiation in details, we will be looking into these concepts at a in more details. And 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 today, what we will do is, if there so I saw the discussion forum. I believe there were no doubts that were posted in the last week. uh, Please actively, as I said, please actively use the discussion forum for so that we can address your doubts effectively. And yeah, so having said that, what we will do today is, we will go into a more details of conduction heat transfer from today's class. As also you have seen in your past week's assignment, that we will be learning rigorously how conduction heat transfer works. We will start something with something which is known as the heat diffusion equation. And what we will do is, basically, will be also, since the Fourier's law is just the basic form of conduction heat transfer, so we will be using Fourier's law very frequently, that we have seen already in the last class how to apply Fourier's law. We will be also learning the fundamental equation which governs, or which dictates how conduction heat transfer actually takes place. And that equation is generally known as the heat diffusion equation. We will be learning all these things by something which is known as a control volume analysis. That is, we will be solving conduction problems using a control volume analysis, because this is one of the basic things uh, that enables us to deal with a problem more formally, and also help us to develop more insights into the problem. So we will be sticking into these concepts of analyzing heat transfer problem using a control volume analysis. And towards the end, we will look into the concept of heat generation. That is, what happens, how does conduction take place, or for instance, what would be the temperature profile, the temperature gradient, and things like that when there is heat generation taking place in the material of interest. Okay, so these are some of the things that will be learning today. And of course, as I said, that we'll learn all those things by solving problems, because this is precisely what this problem solving session is meant for. And yeah, so so let's get started uh, by looking into the first problem. So in your second assignment, that is the assignment that you are supposed to submit, I guess by the last, I guess by next week. That of course is the second assignment. You are exposed to similar kind of problems. So please pay attention to these problems when I solve. And as I say, if you have any doubts, you can either ask in these live discussion sessions, or when you watch these videos later on, then please use the discussion forum to you know to ask your queries, and we will be like happy to address them. Okay, so let's get started with the first problem. So it says that assume certain things. For instance, it says that assume that it's a steady state, a 1D heat transfer problem through a symmetric shape as shown. That is, this is the shape that they have given to us. This is symmetric, and as you can see, this is symmetric about this axis, which is the x-axis. And it further says that there is no internal heat generation taking place. And to this end, what you need to do is you need to derive an expression for a thermal conductivity K for the conditions that your area, so as you can see, although this is a symmetric shape, the cross-sectional area is varying along x, as you can see. And more precisely, when you move along the plus x direction, our area is basically decreasing. Okay. And it tends to 0 when x tends to 1, to be precise. Okay, so given that this is how your area is changing, of course you can see very prominently that your area is changing linearly, and this is the temperature profile that they have given us, with the rate of heat transfer being 6000 watt. All those things are given to us. So what you need to do is what the question asks us is, do we need to derive an expression for a thermal conductivity K of x. So we need to evaluate the thermal conductivity, which is a function of x. That's all. That's all that we need to do in this problem. The assumptions, as they have said, as I repeat, is that consider steady state. It's a 1D heat transfer problem. That we already discussed the consequences of assuming that your heat transfer is one dimensional. Is clearly, I mean, we have seen that clearly in the last class. So that's an assumption that they have asked us to consider. And the shape is symmetric. That's all they have said. And given that your area is this much, your temperature profile is this, and your rate of heat transfer is 6001. So that being said, what they have asked us is to evaluate the thermal conductivity of the material. Now, if you pay a close attention, okay, your thermal conductivity of the material will be a function of x. That is, it will not be constant. Okay, so why I say this is so it will be more clear as we will do the exercise. Okay, but I hope this problem is clear, so as to what we need to evaluate. I'll stop here for a couple of minutes so that you can understand this problem and try to think about like how do we proceed to get towards the solution. Okay, so as I said, the first and foremost thing that we will do is that we will analyze these heat transfer problems by building a control volume. Okay, that is the first step towards uh, towards the solution, towards going towards, I mean before proceeding to calculate what exactly the thermal conductivity will be. We will, I mean, in most of the problem, whenever there is an analysis that needs to be done, we will always start off by building the control volume. Okay, so for this problem, what we will do is we will choose a control volume that kind of encompass the body basically. Okay, so this is how we will build the control volume. Okay, so this is my control volume of interest. And remember, The manner in which you build your control volume is completely up to you. That you may ask me that I can also build a control volume something like this. Okay, I can also build a control volume something like this. So the size of the control volume is completely dependent on who is solving the problem. That's what I can say. But a wiser choice of a control volume is always, essential, because that helps you, that precisely helps you to move towards the correct answer in a more, uh, in a more direct way, I would say. Okay, or in a more clever way, of getting the correct answer. Okay, so despite the fact that that the size of the control volume or the shape of the control volume that you choose is at our disposal, but the choice that we need to do, that we need to make in choosing a control volume, is dependent on how quickly, we get the answer. That's one perspective I can say of on how do we choose a control volume. So for this case, we will choose a control volume which just encompasses the body. Okay, and because the main, so if you ask me why I am choosing like this, the reason would be that the main interest for which we are doing the heat transfer analysis here is the body. It's not the surrounding. So I'm only interested in the mechanism of heat transfer that is taking place in this solid object, and that's the reason why I'm choosing the control volume that just consider the solid object and nothing else. That is, I'm not aware of of anything that is taking place in the environment. Okay, so as I said, the first step is to choose the control volume. The second step, since you are doing this problem for the first time, I will proceed very slowly. The second step is that we always need to write the assumptions that we are considering, although it is given in this problem, but at least we should make it a habit of writing the assumption. Okay, so let's quickly, see the assumptions. So first and foremost assumption that they have already said is that it's a steady state process. Okay, so it's steady state. And the second is, already we have used that in the previous class as well. So it's 1D heat transfer analysis. Okay. And yeah, I think that's it. It's a steady state and it's a 1D heat transfer analysis. So considering this control volume, okay, and given that we consider, these two assumptions, what we will now do is we will apply. So what we'll do is we'll apply energy balance in the control volume. Okay. Energy balance means it's just the first law of thermodynamics. That's it. That energy in minus energy out plus some energy generated is the rate of change of energy inside the control volume. That's exactly the first law that we will use. Okay. So, or it's just the principle of conservation of energy. That's it. Okay. So let's write this. Let's just write this energy balance for this control volume. So if I do that, I can write that the energy that is coming inside the control volume minus, in fact, I would write energy per unit time, which then becomes the rate. So it's the rate of energy that is coming inside the control volume minus the rate that is going out, which is just E dot out, plus rate of change of energy in, the energy that is generated inside the control volume, E dot gen, is equal to, it's like del T of ECV. So it's, so what it says is, so this is typically the most general form. I hope you can appreciate that this is the most general form of energy conservation that you can apply, okay, in any control volume. And that's the reason why we are choosing a control volume in this exercise, because if you choose a control volume, it becomes easier for us, in fact, to apply the equations that uh, equations that are necessary for this analysis. Okay, and that's the reason why a wise choice of control volume is essential in order to proceed the problem in a correct way. Okay, so I hope you are aware of this form of the energy balance. So it's very simple. It just says that the energy that is coming inside the control volume plus the energy minus the energy that is going out from the control volume, and if there is any energy generation taking place inside the control volume, is equal to the rate at which the energy that will change inside the control volume. That's precisely is what the energy balance gives us if we apply this for this particular case. Okay, so here I would also write one more assumption. Okay, oops. So that's okay. So I'll write one more assumption. So this problem also says that there is no heat generation. There is no heat generation that take place inside the control volume of our interest, which means that no heat generation. Okay. So in that context, what we can do is we can say that since this is a steady state, this rate of change of energy inside the control volume, this term would just go to oblivion because it's a steady state. So all the variables won't be a function of time. So this should be 0 because of the, so this is 0 because of assumption 1. And that's typically why you need to write the assumptions, because then, simplifying the equations becomes clearer. Okay. This is because of assumption 1. This is 0. That is because of assumption 3 that we just now said, that there is no energy generation taking place inside, the control volume, which means that this generation term is also 0. This is assumption 3, which means so what we get is it's just that E dot in minus E dot out, that is equals to 0. That's it. So the simplified version of the energy conservation applied for this control volume using all the assumptions that we just now saw is that the energy that is coming in inside the control volume is equal to the energy that is going out outside the control volume. Now, you need to understand that what is the energy that we are talking about for this problem. It is just the rate of heat transfer, right? Because there is no other mechanism which is responsible for transferring energy in this control volume of our interest. Which means if I now say that energy in minus energy out is equal to 0, this will directly imply that the rate of heat transfer is constant. Okay, I repeat, what we did is we applied the energy conservation principle, invoke all the assumptions that we consider, and then we reached at a point which says that the energy in, that is the rate of energy that is coming in inside the control volume, is equal to the rate of energy that is going outside the control volume, which means now since we are only dealing with heat transfer, that means, and since whatever heat that is coming in, so in simplified words we can say that whatever heat that is coming in is equal to the heat that is going out. So the only consequence of this statement is that the rate of heat transfer need to be equal, is constant. Okay, and that is typically the reason why you could see that Q, instead of this way, this is instead of all the, even if all the other parameters are a function of x, you saw that your rate of heat transfer is just a constant, and this is equal to 6000 watt. Okay, so we have now proved by invoking all the assumptions that indeed the rate of heat transfer, even if the area is varying, even if the temperature is a function of x, because of this varying area, your rate of heat transfer is constant. And that is a direct consequence of applying the energy balance, choosing an appropriate control volume in our analysis. Okay, so since this rate of heat transfer is constant, this means we can, and that's the reason why the question says that Q is equal to 6000, and that is already given. I would say we have not calculated it, we have inferred that why this rate of heat transfer is constant. Okay, that directly comes from the energy balance. Now, that is not what the question has asked us. Remember, the question is still, we are still yet to exactly find out what the question is seeking us to find out. Okay, and that is nothing but the thermal conductivity, which is Q of x. So now, since we know that rate of heat transfer is constant and this is equal to 6000 watt, and as the question has said, so what we will now do is we will now apply Fourier's law, because the only relation that gives us the thermal conductivity from the rate of heat transfer is the Fourier's law. Okay, so we'll apply Fourier's law, and the Fourier's law says that the rate of heat transfer is equal to your heat flux times the area. So this will basically become minus K, your thermal conductivity can be a function of X. Area is indeed a function of X, that is given in the question, and dt dx. Okay, and this is equal to 6000, because you already know that your rate of heat transfer is 6001. Okay, so from this step, the way we got this particular form is just by applying Fourier's law. Okay, and remember, and if you remember, when I say that my Fourier's law is equal to minus K, which may be a function of X, Ax times dt dx is equal to the rate of heat transfer. This form of Fourier's law, if you remember the analysis that we did in the last class, this form of Fourier's law is valid whenever we are considering the heat transfer to be one dimensional. Okay, and this is very essential, because the most, if you remember, the most generalized form of Fourier's law is not the but if you remember, it was something like this. It says that your heat flux vector is equal to the thermal conductivity tensor times gradient of temperature. This was the most generalized form of Fourier's law. Okay, but since we have assumed that the problem is one dimensional, we can use this form of the Fourier's law, and we have extensively discussed this in the last class, how this simplified version of Fourier's law comes from the generalized form of Fourier's law. Okay, anyways, so now what we need to do is we need to evaluate this dt dx. We need to evaluate this dt dx in order to find this k of x, but that is known, right? Because your temperature profile is given to us. So your temperature profile is 300 into 1 minus 2x minus 3x cubed, which means since your t as a function of x is what? It is 300 into 1 minus 2x minus 3x cubed. That is your t, which means your dt dx is just the derivative with respect to x. So it just becomes what? It just becomes minus 600 x and what? Minus 900 x squared. That's it. Okay, so this is your dt dx, which means, and of course your area is known. Area is just a of x is what? It is just 1 minus x. And if you just substitute these values over here, what will you get? You'll get minus k of x times of ax, which is 1 minus x, times dt dx, which is minus, so I'll take the minus sign common, which means it will become a plus sign, and then this would become 600 of x plus 900 x squared, and then this is equal to 6000. Okay, which is the rate of heat transfer, which means what? Which means I get my k of x as 6000 divided by 1 minus x times of 600x plus 900x squared. Okay, I think that's it. So if we just do some simplification, and maybe I can take 300 common. If I take 300 common, then what do I get? I get here 1 minus x. This becomes 2x. Or I think, okay, did I make a mistake here? Okay, so this has to be x, right? Because I'm doing a differentiation. So in this step, I'm differentiating this with respect to x. So then this will be x actually. Sorry for that. This is just 600 minus 900 x squared, which means this is just 600 minus 900 x squared, and this is this. Okay. So then this would be what? This would be 300 into 1 minus x, and then this would be 2 plus 3x squared, and then this is 6000, and then this will give you 20. So your thermal conductivity, as you can see, is 20 by 1 minus x into 2 plus 3x squared. Okay. All right. So that's it. That's the answer, that they had asked us. And as you can see, your thermal conductivity, is indeed a function of x. Okay, and that actually is the case. You know why that actually is the case? Because your area, the area was actually decreasing, which means that your heat flux, that's an important thing that we can also appreciate from this problem. Since your heat flux is constant, that we have already figured it out from the energy balance, which means that since your area is actually decreasing, that means I'm sorry, I said it in a wrong way. What I meant is, from the energy balance, since your rate of heat transfer is constant and your area is actually decreasing, which means your heat flux will be a function of x. And since your heat flux is a function of x, your thermal conductivity will eventually turn out to be a function of x, because because of the Fourier's law, to be precise. Okay. So what I was saying is, so that's not been asked in your problem, but you can say that. So the question that I want to ask is, will the flux q double prime in the x direction be a function of x? Now is something that I want to ask. And then this is simple, right? Because you can always write that your rate of heat transfer in the x direction. Remember, when I write a subscript over here, that means it signifies the rate of heat transfer in the x direction, and it says that it is just your flux times the area, right? And now you can appreciate that this is constant. Okay, this is constant from energy balance. This bit is constant from energy balance, which means since your area is essentially decreasing with x, this means your heat flux should essentially increase with x in order to make your rate of heat transfer constant. And that's that's the basic thing, right? So so I hope you can understand this, right? Because see, the left hand side of your equation is a constant, and in the right hand side it is the product of two quantities. Now, one quantity, which is the area, we know that it is varying as 1 minus x, which means if I move along the plus x direction, my area is essentially decreasing, which means in order to make this a constant, my heat flux should essentially increase, or in other words, my heat flux should be a function of x. Okay, and that is typically the reason why from the Fourier's law you can conclude that your thermal conductivity is a function of x. Okay, so that's that's one of the observations that we can draw from this exercise. Okay, I hope you understood this. And but yeah, but as per the question, we just need to calculate this thermal conductivity. But this is just a reflection of what we saw in this problem. Okay. All right. So I repeat, in this problem, although it was a simple problem, there are multiple things that we need to understand when we solve problem associated with heat transfer, and in particular conduction analysis. The first is that, if possible, and if the question demands, always start off by drawing the control volume. This helps us to apply the conservation laws that is necessary for this analysis. For instance, what we did is we very easily, since we pinpointedly described how the control volume will look like, it became much easier for us to apply the energy balance in this case. Okay, and then from the energy balance we concluded that why the rate of heat transfer is constant. The reason is again associated with the assumption, and for that you also need to pinpointedly write what assumptions you are considering in your analysis. And this is I would say one of the most important steps while you are solving problems, especially when you are I mean, in multiple choice you don't have to do all these things, but when you're sitting for a written exam, where actually you need to use your pen and paper to actually write the problems solve the problems in details, showing the steps, then all this analysis becomes, all this points become necessary, and that is when you make your analysis more complete. Okay, because see, you could have just started from this point and then just find out an expression for kx. There is nothing wrong in that, but this makes the entire analysis incomplete, because you cannot justify that why you have chosen your rate of heat transfer to be constant, and such important stuff that are associated with the given formulas that we always use in our problems. Okay, and that's the reason why you always need to start off in the same procedure that I just now showed in this exercise. All right, so I'll stop here for a couple of minutes. If you have any questions, you can ask, or else we will move along to the next problem. Okay. All right. So let's then see the next problem. So what the problem says is a solid truncated cone serves as a support for a system that maintains the top truncated face at the of the cone at the temperature T1, which means that the top face of this truncated cone, as you can see, this is at a temperature T1, and the area of this surface perpendicular to the x direction, which you can see, is A1. Okay, while the base of the cone is at temperature T2, which is less than T1, meaning that when we move along the x direction, my T2 is less than T1, which means that as and when I move along the plus x direction, my temperature decreases with x. That is something that you can infer. Okay. It then says that the thermal conductivity of the solid depends on the temperature according to the relation K equal to K naught minus AT, where A is a positive constant. They have not said anything about K naught, but you can say that A is a positive constant. You can, I guess, without the loss of generality, you can assume that K naught is also positive. Okay. All right. Given that, and they have said that the sides of the cone are well insulated, which means, see, this is now an indication of the fact that your rate of, I mean, your heat transfer is one dimensional, because since these faces are insulated, that means there is no way heat can pass in this direction, which means the only way heat transfer can take place in this case is in the x direction. Okay. Now, given this scenario, they asked us, do the following quantities increase, decrease, or remain the same with increasing x? Okay. So what we need to evaluate is, when I move along the plus x direction, how does rate of heat transfer change? How does the heat flux change? How does the thermal conductivity change? And how does the temperature gradient change? Okay. In other words, we just need to evaluate the variations of the rate of heat flux, the the variations of rate of heat transfer, the heat flux, the thermal conductivity, and the temperature gradient when we move along the plus x direction. Okay, this is what we need to evaluate from this problem, and and yes, so I would say this is a similar problem to the one that we solved it uh, earlier, but this, I would say, is a more involved problem, because they have not only asked about the thermal quantity, rather they have asked us about all the quantities that are involved. Okay, for instance, in addition to the thermal conductivity, they have asked us how the rate of heat transfer changes. This also we have analyzed, but again we will do that once again for this exercise. And they are also asking now how the temperature gradient dt by dx change along the plus x direction when we move along the plus x direction. Okay, so first thing first, you need to understand the problem. What it says is that this T1, which is the top surface of this truncated cone, is greater than T2, meaning that your temperature decreases with increasing x. This is the first step. The second step is that these faces are insulated. These faces are insulated, which means that your rate of heat transfer is one dimensional. Okay. Again, this is an assumption that we will invoke. Okay. And given this scenario, and also, your thermal conductivity also varies something like K naught minus A times T, where this A is a positive constant, and this they have given. Okay. And given this, what we need to find is how does, so as we move along plus x, okay, we just need to evaluate how does these quantities varies basically. So the first quantity is qx, that is the rate of heat transfer. The second quantity is heat flux. The third quantity is thermal conductivity, and the fourth quantity is dt dx. How these quantities vary is what the question has asked us to find. Okay. All right. So the first thing first, as I said, we will begin this problem by drawing the control volume, and as we did in the last problem, the control volume that we will draw will be something like this. This will just encompass the surface of the truncated cone. Okay, and this is going to be my control volume. Okay, then I think now you can at least understand the chronology of things. So the second thing is we'll see the assumptions. Okay, so the first assumption is then, so it's straightforward that your heat transfer is one dimensional. Okay, second, you can argue that this is a steady state analysis. Okay, all right, so given we consider these assumptions, and of course you can also say that there is no heat generation inside the control volume. And just considering this assumption, you can now apply. So this is something that we already did, so we need to apply. Okay, apply energy balance in the CV. Okay, and if we do that, I'll not once again store the entire stage because this we have already did in the last class. I mean, sorry, in the last exercise. So you can show that if you apply energy balance inside the control volume, you will eventually get E dot in, the rate of change of energy. I mean, sorry, the rate of change of energy. Sorry, I mean the energy that is coming inside the control volume minus the energy that is going out from the control volume is equal to 0. Okay, that is typically because there is no heat generation, so the heat generation term basically is 0, and it's a steady state process, which means that del T of ECV is 0, which just means that E dot in minus E dot out equal to 0, and this is a straightforward conclusion that your heat flux, sorry, your rate of heat transfer, your rate of heat transfer Q in the x direction, because this is a 1D heat transfer problem, is constant. Okay, so that's the first answer to our problem. That is, when we move along plus x, my q of x does not change or is constant. Okay, all right, that's the first objective that we solve. Second, let's see now how does the heat flux change. Okay, the second thing is how does the heat flux, which is qx double prime, vary along x. Okay, and as you guys know, we will use the much celebrated Fourier's law. So it just says that your rate of heat transfer qx is constant, that we have already argued from this point. Okay, which means if we now apply the Fourier law, it will say that what? So it will say that minus k, which is a thermal conductivity. Okay, so let's not use the Fourier's law now, because Fourier's law will not give us the flux, because it will in turn give us the relationship between the thermal conductivity and the temperature gradient, which we'll do it later on. Eventually we need to use the Fourier law, but we can now use a very simple argument that since your qx is constant, but you know that your rate of heat transfer is your flux times the area, because that's obvious, right? The rate of heat transfer is what? Your heat flux is watt per meter square, which means that your rate of heat transfer is going to be flux times the area, which means I can now say that my heat flux Qx, which is the rate of heat transfer, is just the product of Qx double prime times your area, but your area is a function of x, that we all know, and this is constant. And we now know that as we move along the plus x direction, okay, what happens to the area? This is something that we will see. So when we move along the plus x direction, I know that my base area, which is A2, is larger than the top area, which is A1, and this is already given, which means when I move along the plus x direction, my area, which is a function of x, it is actually increasing. Okay, so when I move along the plus x direction, my A of x is increasing, which means it's the same argument that we have used in the last problem, that since your Ax is increasing, in order to make this as a constant, your heat flux should decrease. Okay, so for rate of heat transfer to be constant, the heat flux decreases with increasing x. Okay, and that's how your Qx vary along the x direction. Along, to be precisely, that is how Qx vary along the plus x direction. Okay, and see, you can now draw very nice analogy from the previous problem. In the previous problem, if you remember, the surface or you can say the control volume was something like this, which means that when we move along the plus x direction, my area, which was a function of x, was decreasing, and that's the reason why my heat flux was essentially increasing in that scenario. Okay, but in this case, when we moved along the plus x direction, our area, because of the fact that your rate of heat transfer is constant, our area is essentially increasing with x, which means that now in your case your heat flux will essentially decrease with x. Okay, and and that's again because of the fact that your rate of heat transfer is constant, which means for the right hand side to be equal to constant, if this quantity increases, and this quantity has to decrease in order to maintain the balance, so that the right hand side basically stays as a constant. Okay, and that's the argument that we have used here also to basically argue how the heat flux changes with x. Okay, I hope you understood this point. Okay, so next let's see what they have asked us. So we have calculated how the rate of heat transfer varies along plus x, how the heat flux varies along plus x. Now let's look at the thermal conductivity. Okay, so what they have said, so they have said that the thermal conductivity is not a constant, but rather it's a function of temperature, which has this particular form, which is k naught minus a times of T. Okay, so the thermal conductivity K, it can be a function of x, it can also be a function of temperature, but in this particular problem they said that the thermal conductivity is not a function of space or x, but rather it's just a function of temperature. So K, which is a function of temperature, is like k naught minus a times T. Okay, but we know that so what do we know? We know that this T is essentially a function of x, which means implicitly you can say that your thermal conductivity, which shows dependence on temperature, and because your temperature is also a function of x, your thermal conductivity is also a function of x. Okay, I repeat, in the problem they said that my thermal conductivity is a function of temperature, which is k naught minus a times T, but we know that this temperature itself is a function of x, which means, and why is that, why the temperature is a function of x? That is simply because the top surface and the bottom surface are at two different temperature, which means that your temperature should vary along the positive x direction. And since my temperature is a function of x, this implicitly implies that my thermal conductivity will also be a function of temperature, and it is also a function of x. Okay, all right. So now, in order to evaluate how your thermal conductivity will vary along the plus x direction, we just need to see how my temperature varies along the plus x direction. And that is straightforward, right? Because we know that, so what do we know? We know that T2, that is the temperature at the bottom at the bottom face of the cone is higher than T1, which is this, that they have already said to us, which means when we move along the plus x direction, when we move along plus x, my temperature, which is a function of x is increasing, and this is because T2 is greater than T1, which means since A is constant, or you can say A is a positive constant, okay, if we move along the positive x direction, I know that my temperature will essentially increase, but there is a negative sign in front of it, and assuming that k naught is the constant, k naught is a, you can say k naught is a positive constant to be precise, this means that when I move along the plus x direction, meaning that my temperature would increase with x, but there is a negative sign in front of it, and I know that a naught is a positive constant. This means that my thermal conductivity should decrease with x. Okay, I repeat the things that I just now stated. We have figured out that when we move along the plus x direction, my temperature would essentially increase with x, and this is already given to us in the problem. And we know the functional form of thermal conductivity, I mean how it relates with temperature. And we also know that this A is greater than 0, meaning that when I move along the plus x direction, this particular quantity would increase, but there is a negative sign in front of them, which means that when I move along the plus x direction, and I'm assuming that k naught is also a constant, this means that when I move along the plus x direction, my thermal conductivity should decrease with x. Okay, so my kt of x, this will decrease when x increases. Okay, and of course you can argue that you can say that what happens when the magnitude of a times t of x exceeds, if this magnitude exceeds beyond k naught, then what will be the case? So we are assuming that this k naught is, so there is also one more inherent assumption, that this magnitude of k naught is much larger than a times t of x, the magnitude of a times t of x. Okay, which means that this quantity would always be subsided by this quantity. Again, it's a way of saying that when x increases, you know even if this quantity basically will lower the thermal conductivity, it will not so happen that the absolute value of this will exceed the absolute value of k naught. Okay, so this is one more assumptions that you can infer when you make this statement that your thermal conductivity will decrease with x when you precisely move along the plus x direction. Okay, all right. So yeah, so that's how the thermal conductivity varies. I hope you are with me with this so far. And finally, they have asked us to evaluate how your, so the fourth point is how dt dx vary along plus x. Okay, and for this we will use our good old Fourier's law, which says that, so let's use the Fourier's law now. So it says that your heat flux is equal to minus k, which we know that now this is a function of x and t, because your temperature so since your temperature is a function of x, this means that your thermal conductivity will in general be a function of x and t times of dt dx, and this is from the Fourier's law. Okay, all right. So now what you can say, so you can say that your heat flux is proportional to your k, which is the thermal conductivity. In general, this is a function of x and t, and it is also proportional to, you can say, that dt dx. Now of course this minus sign comes because this is an important thing. I hope this has been discussed in the theory classes, that why this minus sign comes. That's typically the reason, because since the dt dx, basically the reason is that heat transfer takes place in a direction of decreasing temperature. Okay, so so basically if we evaluate this dt dx term, it turns out to be negative. So in order to make heat flux a positive quantity, because saying flux negative is like it doesn't make any physical sense. So in order to make heat flux a positive quantity, this minus sign basically pops up as a consequence of that. Okay, and this is a question in your assignment, that why there is a minus sign actually in Fourier's law. Okay, but the magnitude of flux, if you try to see that how is the magnitude of flux vary along the positive x, I can say that it is proportional to the thermal conductivity k, and it is also proportional to the magnitude of, you can say, dt dx. Okay, so I am just discarding the minus sign because I am only interested in knowing how. I just want to know that how my qx double prime, basically the flux, vary along the positive x direction. Okay, and that's the reason why I am just dealing with the magnitude of dt dx and not just the sign that is associated before it. So now we just need to see how these two individual quantities vary along, plus x, to see how this flux basically vary along the positive x direction. So now you just need to tell me that when we move, so along plus x, my k, the thermal conductivity, we just now saw that this basically decreases. This basically decreases. Okay. So along plus x, my thermal conductivity. Did I make any mistake here? Okay, when x increases, your hold on. Just 1 second. Okay. Okay, I'm very sorry. I guess I made a mistake here. So I was of the other way around. So it says that your temperature is actually decreasing along the plus x direction because your T2 is less than T1. Okay, I'm sorry for that. Which means that, so what does it mean? It means that your along plus x, your temperature is actually decreasing. I'm sorry, I just made this mistake. Since your T2 is actually less than T1, that's what the problem has stated. Your T2 is actually less than T1, and this means that this will be the other way around. Your thermal conductivity will essentially increase along the plus x direction because this quantity is decreasing and there is a minus sign in front of them, which means that when this quantity will decrease, eventually this will basically increase along the plus x direction. Okay, that's the thing. I'm sorry for that. I just overlooked it. Okay, so along plus x, I just now stated that k, which is the function of x and t, this increases, and we also know that dt dx. Okay, so what happens to dt dx? Okay, so all right, so now this is interesting. So let's see what happens to dt dx. So we can say that when we move along the plus x direction, your temperature is actually decreasing. Okay, so since your temperature is decreasing, that means you can say that your temperature gradient will also decrease with x. Okay, which means that my dt dx should also, this should also decrease with plus x. Okay, which means that my okay, no, I think, all right, so they're asking about this. Okay, so I think it is more convenient to see. Okay, so I think it's more convenient to see this from the heat flux perspective. Okay, because we have already said that when we move along the plus x direction, my heat flux is decreasing. That is typically because the rate of heat transfer is constant and your area is increasing, which means your heat flux should decrease. So I know that my along plus x direction, I know that along plus x, my q double prime of x, this is decreasing. Okay, which means that I have a quantity where this term is decreasing and this is equal to a term where this is also decreasing, which means that my dt dx, at least its magnitude. So from these two observations, I can say that my mod of dt dx should also decrease with plus x. I made a little bit of confusion here, so I'll clarify things out. So what they're asking us is that how is the temperature gradient varying along the plus x direction? So what we did is we just applied Fourier's law and we just checked, in order to evaluate how the temperature gradient varying along the plus x direction, we just need to see how thermal conductivity and the heat fluxes vary along the plus direction. I was telling this thing the other way around, okay? But the fact that we already know that my heat flux, and we already know how the thermal conductivity and the heat flux vary along the plus x direction, which means that this is sufficient to tell us what this dt dx would be, how this dt dx would evolve typically. And for that, we know that my thermal conductivity was increasing with respect to x. That was typically because your temperature was decreasing. And we also know that your heat flux was decreasing. The reason behind this was again because of the fact that your area was increasing with respect to x. Okay, which means that I now have a quantity where the left hand side is decreasing with plus x. The right hand side was also decreasing with plus x, which means for this balance to be established, your dt dx should in principle decrease with respect to decrease when you move along the plus x direction. Okay, so that's the answer. So your dt dx should decrease when you move along the plus x direction. Okay, I just made a made a little mess about it, but that's the clear picture. Okay, so I repeat, we will just use the Fourier's law to basically see how, you know, dt dx, that is the temperature gradient, vary along the plus x direction, because we already know how the heat flux and the thermal conductivity change or vary when you move along the plus x. We saw that the thermal conductivity, you know, decreases along the plus x direction, while the heat flux also decreases along the plus x direction. Okay, the individual regions we have already witnessed when we saw, when we looked into these quantities individually. But since these quantities decrease along plus x direction, and their you know, their relation is established by something like this means that dt dx should also decrease if we want to maintain this equality, to be precise. Okay, and that's the reason why when you move along, you know, the positive x direction, that is when you move along the surface from the top surface to the bottom surface, your temperature gradient will actually decrease with x. Okay, we don't need to see how the temperature varies, but rather the knowledge of the heat flux and the thermal conductivity is sufficient to give, or to infer how your temperature gradient varies along the plus x direction. And that typically comes from the Fourier's law that we have used here. Okay. All right. I'm very sorry for the confusion that I created, but I think now the picture is clear at your end. Okay. All right. Once again, we'll stop here for a couple of minutes. I hope this problem is clear. This is a good problem actually, and this will clear all your, you know, this will clear all your concepts related to, you know, Fourier's law, how to build a control volume, and how to analyze quantities pertaining to, you know, conduct and heat transfer. At least so here we did not do any quantitative analysis, but at least qualitatively, just by looking, you know, how different quantities varying along x, and by using Fourier's law, we can see how the associated quantities also vary along that particular direction. Okay. Of course, staying in the regime of one-dimensional heat transfer and steady-state analysis. That's the assumptions that already we have uh, taken into our analysis. I mean, taken into the consideration. Okay. So I hope you understood this problem. Please let me know if there are any confusions. And if you have any questions, you can feel free to post anything related to these things in the discussion forum, and I'll be happy to address them. Okay, so moving on then, let's move into the next problem. And the next problem, I would say it's even more interesting, and this is related to something which is known as heat generation in slabs. I think you got the picture of this when you were looking into the lecture series of this week. That how do we utilize the concept of heat generation into conduction analysis? Okay, so before me, you know, reading out the problem, I would ask you to go through this problem, and I have also drawn the schematic for you below, as you can see on your screen. Please go through this problem once, and then I'll discuss the nuances of it. Okay, so let's look into this problem. So it says that a one-dimensional plane wall of thickness twice L equal to 100, meaning that this length is 100 mm, experiences uniform thermal energy generation of Q dot equal to 1000 watt per meter cube. Okay, so there is a source which generates energy inside this slab. We are not essentially bothered about how this energy is generated. Rather, we are bothered about what will be the consequence of this energy generation into the heat transfer analysis. And that's the reason why they have said that they have just given us the information of, the magnitude of energy generation taking place per unit volume inside this slab. And while this energy generation is taking place, the slab will now try to dissipate energy to its ambient, due to which in order to effectively uh, felicitate this process, there is convective cooling at the edges, or at the faces, you can say, of the slab. Okay, and this convective cooling is being carried out by an ambient fluid. Okay, you may consider it as water, whose temperature is 20 degrees Celsius. Okay, so in order to give a better view of the problem, you can think of it like there is a heater that is inside a slab. Okay, there is a heater, and this heater is generating heat inside this slab. Now in order to dissipate this heat, because of, let's say, certain material restriction, you are cooling this slab from from you are basically cooling the faces of this slab by using an ambient fluid whose temperature, you can say that the temperature of this ambient fluid is equal to 20 degrees Celsius. Okay, that's what the problem has stated us until now. Now it says that if steady state temperature distribution within the wall is T of x is something like this, that they have given to you, that they have given you the temperature distribution inside this wall. Okay, and the values of A and B are given. They have asked us, first of all, what is the thermal conductivity of the wall. That that is something that they have asked us. And the second thing is that we now need to evaluate the value of the heat transfer coefficient H. Okay, so two things we need to do given this scenario: that we need to find out what is the thermal conductivity of the wall. The second thing, what is the heat transfer coefficient of associated with the flowing fluid, okay, which is used to cool the faces of this slab or wall, whatever you wish to say. But to this end, they have given us what is the temperature profile inside this slab, and they have said that the temperature profile is something like this: A into L square minus x square plus b. And the coordinate system, you can see it from your screen, is just so the coordinate system is just fixed at x equals to 0, which means that the faces of the walls are at x equal to 50 and at x equal to minus 50. And surrounding fluid, of course, is at temperature 20 degrees Celsius. Okay, so given this scenario, what you need to do is you need to find number one, the thermal conductivity of the slab or the wall material, that is K. And second, the heat transfer coefficient associated with the flowing fluid. That is something that we need to find. And and yeah, all right, so we'll do the analysis of this problem. But again, I want you to just go through it once and try to observe certain things that we can infer, at least from the temperature distribution that they have given to us. For instance, can we say that this temperature distribution is symmetric about x equals to 0? Okay, this is one important observation that we can try to figure out. For instance, if you put x to be equals to 0 in the temperature distribution, so let's first have a look at the temperature distribution before going into the further analysis of this problem. So what I'm saying, that x equals to 0, that is when I'm inside the center of the slab, that is over here. Okay, what does T of x become? So T of x at x equals to 0 is a L square plus b. Okay, So let's say this is some value that we kind of get it here. Now, an important observation is when we move along either of plus or minus x. So this is something that is important. Please try to understand that when we move either in the plus x or in the minus x direction, the temperature that we will get, okay, is exactly going to be when I am in this region, that is, let's say at a point x1, or I am at a point, let's say minus x1. That is typically because the dependencies is the dependence of temperature on x, okay, is x squared, which means either x can be positive or negative. The temperature will always be the same if I am at a location which is either x1 or minus x1 inside the slab, to be precise. That is, I am always inside the slab. I am not bothered about the temperature distribution in these areas. All I am just saying that if I am inside the slab, and let's say I am at a coordinate, let's say I am at a coordinate x1 and I am at a coordinate, let's say minus x1, the temperature that I will get, just by substituting the value of this coordinate is exactly going to be the same, which now means okay, which now means that your temperature profile has to be symmetric about the center line. Okay, so this is typically the hallmark of a parabolic distribution, and you can prove that whenever there is heat generation taking place and heat is being dissipated equally uh, from both these sides, your temperature profile will always be a parabola, and it will be symmetric about the center line, given that your thermal conductivity is constant. Okay, your thermal conductivity should not be a function of x. This is something that you need to understand. Okay, meaning that let's draw this picture in a better way. So what I'm saying, that your temperature distribution will be kind of something like this, with it should be something like this, with the value at x equal to plus L is exactly going to be the value at x equal to minus L. Okay, and that you can appreciate, right? If you put here x equal to L, then this term will go to 0. If you also put here x equal to minus L, then also this term will go to 0, which means that at x equal to plus and minus of L, my temperature at x equal to plus and minus of L is just going to be B. Okay, so here the temperature was what? It was A L squared plus B, and here the temperature is B. So two things we can infer. First, the temperature distribution is parabolic because there is a heat generation taking place, and you can also prove, I think this you did this in the theory class, that if the thermal conductivity is constant and if there is and if there is heat generation taking place inside the rectangular slab, then, and of course that heat is getting dissipated equally from both its sides, then you can prove that your temperature distribution is a parabola. Okay, of course in the regime of one dimensional heat transfer analysis and steady state uh, conduction taking place in the picture. Okay, so this is how your temperature would essentially vary along the so this is how your temperature distribution would look like inside the slab. Okay, so so these are just 2 points that I was showing. Okay, but the second conclusion is even more interesting. The second conclusion, it says that at the at the center line of the slab your temperature is highest. Of course that you can appreciate by substituting x equal to 0, and you can see that when x is equal to 0 your T is maximum, and as you move either along the plus or minus x direction, either way is just the same as we just now saw, your temperature will eventually decrease from what was its value at the center line. And that is obvious, right? Because it says that there is a heat generation taking place inside the slab. So what this heat generation would imply, that it will generate the maximum heat inside the slab, and since there is a cooling fluid that is basically convectively cooling the slab from its sides, your temperature would eventually decrease when you move along the edges. When you move along the edges of the slab. Okay, so you are bound to have a maximum temperature inside because heat needs to be dissipated. So as you move along, as you move from the center line towards the edges, your temperature would eventually decrease, and it will basically symmetrically decrease, and it should reach to a point where it will be at the lowest at the edges and maximum, at the center line. So from the temperature profile itself, without doing any further analysis, but remember, as I said, these things are true under the assumptions that, so these things are true under, the assumption that your K is constant, okay? Your Q dot, that is, or I would say it's not, okay, so this heat generation, I would call it as not Q dot, but as Q double prime, because this is a volumetric phenomenon. So this Q double prime, which is my heat generation, this is constant. That is heat generation, that is the heat that is being generated inside the slab is just the constant value. Okay. And of course we are in 1D heat transfer analysis. 1D heat transfer and steady state. Okay. And steady state. Okay. Under this scenario, you can get these specific features of the temperature profile that we just now saw. Okay. I hope this is clear. So this is the preliminary things that we can infer just by taking a close look at the temperature profile. Alright, now the objective is to calculate first the thermal conductivity of the wall, and for this there are two approaches to calculate this. One by directly using energy balance. Second by something which is more formal, and I would say from the heat diffusion equation that you guys have just now derived in your lecture classes. So what we'll do is we'll use the second one, that is the more formal way, and then if we have time, I will show you that also by applying energy balance there is a shortcut way of calculating what will be the heat transfer coefficient of the fluid. Okay, and of course the thermal conductivity as well. So but I would say that's a second way. I would say it's not a shortcut, actually it's a second way of doing it. But first we will utilize the heat diffusion equation to calculate what will be the thermal conductivity of the slab. Okay, so we will use the heat diffusion equation to calculate K. So the most general form of the heat diffusion equation is something like this: del x of Kx del T del x, okay, plus del y of Ky del T del y, plus del z of Kz del T del z, okay, plus Q double prime, that is the heat generation, is equal to rho Cp del T del T. Okay, so this is the most general form of the heat diffusion equation, and I hope you have derived this in, and I'm sure that this has been derived in the theory classes. But the idea is very simple. You get this, so you get this form by simply doing an energy balance analysis inside this slab. Okay, and when you do that in the limit where so all you need to do is you just need to choose control volume something like this, which has an elemental thickness of dx. Its volume is basically dx dy dv, and all you need to do is just do an energy balance analysis. That is the energy coming in inside that infinitesimally small amount dx, infinitesimally small amount small control volume dx dy dz. All you need to do is you just need to do that energy balance, and when you do that, and typically this is what you did in your theory classes, you will eventually get this equation, which is known as the heat diffusion equation, and it just portrays how your temperature essentially varies when there is conduction taking place inside a rectangular slab or in Cartesian geometries. Okay, so this is what the heat diffusion equation typically says to you. Now in the limit, or in under the assumptions, so under these assumptions that I just now stated, you can show that your heat diffusion equation simply boils down to K times d2T by dx2 plus Q double prime to be equal to 0. The reason behind this is because of the fact that this term will go to 0 because it's a steady state. These two terms will eventually be 0 because your temperature, that is because your Your problem is a one-dimensional heat transfer problem, which means that your T is just a function of x, and you are saying that your thermal conductivity is constant, which means that this will come out of the derivative. So if you do this, and of course, since this is a one-dimensional problem, your partial derivative, the del x, would get converted into ddx. And if you do all these things, that's very easy to show that your eventually this is how your heat diffusion equation this is typically how your heat diffusion equation would be in the present scenario. Okay, now everything is just given to us and we just need to evaluate this thermal conductivity. Now why is that? That is typically because we know what is q double prime. That has been given to us because the heat generation is given as 1000 watt per meter cube, which means I know that my q double prime is 1000 watt per meter cube. Okay, my temperature profile is also given. Okay, that is from where we did all the analysis. So my temperature profile is given as something like this. So it is given as a into L square minus x square plus b. So it is a into L square minus x square plus b. Okay, which means I can eventually calculate what is dt dx. My dt dx would be minus of twice of ax, and then I can calculate what is d2t by dx2. It would be just twice of a, if I'm correct. Yeah. Okay. So this means that I know what is d2t by dx2. It is just twice of a. I just need to substitute the values. Okay. So this then becomes, so this equation then just becomes minus of k times 2a plus q double prime, that is equal to 0, which means that your thermal conductivity is just q double prime by twice a. That's it. You just need to substitute these values to get the value of thermal conductivity. So we know that q double prime was 1000, but remember this unit is watt per meter cube, and a, that is this length, that we call it as a. Oh, sorry, a is given as 10. I'm sorry. This a is basically given as 10. So twice of a would be 20. Twice of a is 20, which means that your k, that is your thermal conductivity, is 50 watt per meter Kelvin. That's it. That's typically is the value of your thermal conductivity. Oops. Sorry. Okay. So I hope you have understood this. So what did we do? We just applied the heat diffusion equation, invoked all the assumptions that we considered. The heat diffusion equation typically looks something like this. The temperature profile was known, and and from that we evaluated d2t by dx2. The heat generation was also known, and from there we evaluated the thermal conductivity k, which just came out to be 50 watt per meter Kelvin. Okay, so that's it. So let's now do the second part. Let's now do the second part of our analysis, which says that what would be the heat transfer coefficient, the heat transfer coefficient h. Okay, all right. So now you need to pay a close attention. So so try to understand that at least inside the slab up to its edges we have seen how the temperature profile varies. Okay, it's a parabola because it's given because of its certain form, and I have also argued that if the thermal conductivity is constant under steady state and under 1D heat transfer, if there is heat generation, if there is constant heat generation taking place inside a rectangular slab, then your temperature profile is essentially a parabola. Okay, and you have also seen that in the Weeks constant in the Weeks lecture series. Okay, but now all this has to do with the temperature distribution inside this particular slab. But if you ask me what will be the heat transfer coefficient of this fluid, I need to know what precisely happens at the interface of this slab and the fluid. typically at these two edges. Okay, so in order to calculate H, okay, I need to know precisely what boundary conditions, these are known as boundary conditions. So what boundary conditions should I use at the interfaces of the solid and the fluid. Okay, and since this is symmetric, you can do the analysis either at x equal to L or at x equal to minus L. Okay, so let's I mean, without the loss of generality, let's have a look at what happens at x equal to L. So at x equal to L is an interface. First of all, I call this an interface because this is the boundary that demarcates from the fluid to the that demarcates the fluid and the solid. So at x equal to L, remember, at an interface, if there is no phase change that is taking place, your heat flux is constant, your temperature is also constant. So so these two things you need to understand, that at interfaces considering that there is no phase change, okay, first thing, your temperature, your T, the temperature profile T of x is constant, or I would say, sorry, it's not constant, I should rather say it is continuous, and your heat flux is continuous. This is always the case if there is no phase change. Remember, whenever there is phase change taking place, the first statement, this will always hold good, but in second statement there will be a jump in your heat flux. Okay, so this is not true. So this is not true for phase change phenomenon. But your temperature, irrespective of phase change taking place in an interface or not, your temperature will always be continuous. Okay, all right. So but since we are not dealing with phase change as of now, all these so these two observations will hold good. Okay, so now in order to evaluate H, you need to look very carefully at these fluxes. So what basically is happening is that because of this heat generation, there is a flux that is moving in, so eventually there is a heat transfer that is taking place from the slab to the surrounding fluid. That means at the interface, I can say that the flux that is coming from the conduction side should be equal to the flux that is going from the slab to the fluid. That is, the conduction flux at x equal to L or at x equal to minus L should be equal to the convection flux. Okay, because at these two interfaces there is no phase change that is taking place. Okay, so I can say that at x equal to L, my conduction flux should be equal to the convection flux. Okay, and this is just the mathematical statement of this point 2 that I just now stated. Okay, and this is true because all these scenarios there is no phase change that is taking place at the interfaces. Okay, so now what is the conduction flux? So the conduction flux is just the Fourier's law, right? It is just k times of dt dx. But remember, we are evaluating this at the interface, so this becomes minus k times dt dx at x equals to L. This is very important because we are doing this where, so remember, we are equating this q conduction equal to q convection at x equal to L. And because of symmetry, you can also do the same analysis at x equal to minus L and you will just get the same answer. Okay, so that's the reason why when you are applying Fourier's law, we need to specify where you are applying basically this Fourier's law. And now we are saying that this q conduction or like q double prime of x conduction is just minus k times dt dx at x equal to L. And the convection flux at x equal to L, we all know this comes from the Newton's law of cooling. This is just heat transfer coefficient times your temperature at x equal to L minus T infinity. That's it. That is sufficient to tell you what would be your H. Why? Because we know the temperature profile, because we know that your T as a function of x, this is, so what is t as a function of x? So t as a function of x is a l squared minus x squared plus b. Okay, and we have also evaluated dt dx. We have also evaluated dt dx. So dt dx is just minus of twice a. Okay, which means my t at x equal to l, this would become just b, because you just need to substitute here x to be equal to l. Okay, and my dt dx, at x equal to l, this becomes minus 2 times of a times l. Okay, and then what? And then just let's just substitute. So okay, so that's it. So then this is what? This is just b. Sorry. So let's see what b is. So b is just 30. Okay, so this means this is 30. This is your temperature at x equal to l. This is 30. T infinity is 20. And then K, thermal conductivity, we have just now calculated. This is just 50. And dt dx at x equal to L is just minus of twice AL, which is just minus 2 times of A. So what is A? A is given to be equal to 10. So this is 10 times L. You know that L is equal to 50 mm, I guess. Yeah, L is basically, so L is this length because the entire length is twice L, meaning that L is just 50. So this becomes 50 into 10 to the power minus 3. Okay. So that's it. So if you substitute these values, this will typically be, minus 50 times. So this will become plus because there is already a minus sign here. So this is 50 times. So I'll just remove the plus, and then this becomes 2 into 10 into 50 times of 10 to the power minus 3. And then this is equal to, so I'm just writing this. I'm just using this. Okay, please don't get confused. I'm just substituting the values into this equation. I'll call it as 2. So this is 50 and all these things are there. H is something that we need to calculate, times 30 minus 20, which means that your H, that is the heat transfer coefficient, will just turn out to be, so if you do this, so this is what, 50 into 2 is 100. So let's calculate this. 50 into 2 is what? 100. 100 into 10 is 1000. This 1000, this 1000, and this 10 to the power 3 would get cancelled, meaning that this would be just 50 by 10, which means it will be just 5 watt per meter square Kelvin. And that precisely is the value of your heat transfer coefficients. That's it. That's exactly is what your heat transfer coefficient is. Okay. All right. I hope this is clear. Uh, yeah, that's it. That's precisely the heat transfer coefficient. It's 5 watt per meter square Kelvin. Okay. I hope this is clear. So this is a very good problem. First of all, you learn to use the heat diffusion equation, and more importantly, you learn to sketch what the temperature profile would be in case of this scenario when there is a constant heat generation taking place in a Cartesian object or a rectangular slab. Okay, without I mean the heat generation being constant, and steady state picture being taken into account. That's the first thing. The second thing, you learn to use the heat diffusion equation, and it's formed when we invoke all the assumption of let's say steady state, constant heat generation, constant thermal conductivity, and all those things. And then you learn basically how to use boundary conditions on the interfaces. Okay, so for this you need to know how various quantities behave at the interfaces, and these two things are more important uh, when you apply boundary conditions at the interfaces. Okay, and then we apply this, and we just say that the flux coming from the left hand side is equal to the flux that is going on to the fluid, and then the flux coming on from the slab is the conduction flux. The flux that goes into the fluid is is the convection flux, which comes from Newton's law of cooling. Typically, because the areas are same, you can also argue that the rate of heat transfer from conduction is equal to the rate of heat transfer due to convection. That is also something that you can say. And from there, we just evaluated the only unknown that we need to calculate, that is H. Okay, so so that's the thing that I wish to convey. And as I promised, I said you that there is a shortcut way of finding, or I would say it's not a shortcut, it's a second, so there is a second route that we can use for finding out this heat transfer coefficient, but that route will not give you K, typically because we cannot utilize the conduction concept. I guess I typically, because we cannot utilize the fact that we cannot utilize the Fourier's law there. But anyways, that will give you H. So if in the question someone asks you just to calculate the heat transfer coefficient, you can calculate that using just the back of the envelope calculation. Is kind of like that. Okay. So we will end this class by seeing that route, or that step. But in order to understand that step, we need to again figure, I mean draw a control volume, as I was saying you. Okay, so what you need to do is, let's say we are given the same scenario, that is the same problem, and we are now just asked to calculate what will be the heat transfer coefficient. Okay, so without the knowledge of the temperature profile, you can calculate what is the heat transfer coefficient just by knowing how much is the heat generation, and of course the entire dimensions of the slab. And for that, what you can do is, you can consider again a control volume which just encompass this entire rectangular slab. And what we will now do is, we'll apply the energy balance inside this control volume. Okay, so this is the second method, and you can do this at the back of an envelope. So it's just a two-step method. So what we'll do is, we'll apply energy balance. So if we apply energy balance for the control volume, we can see that the E dot in minus E dot out, that is the most general form, plus the energy that is generated is equal to 0, because it's a steady state thing. So I'll not write the unsteady term because it's steady state. So I'll just say that the right hand side is just 0. Now we know that there is no energy that is coming out inside the control volume, because whatever the heat that is being generated inside the rectangular slab due to heat generation, it is dissipated out to the ambient fluid, meaning that whatever the heat that is generated, that is E dot gen, is equal to E dot out. Okay, so now we need to be little bit wise to calculate these quantities E dot out and E dot gen. See, E dot gen is simple, because we know the heat generation per unit volume, the heat generation term per unit volume is Q double prime, and that has been given to us as 1000 watt per meter cube. So if I multiply this by the volume of the slab, this will give me how much is the total energy that is generated inside the slab. So E dot gen, in other words, is just going to be Q double prime times the volume. That's it. So this this left hand side is just going to be Q double prime times the volume of slab. Okay, and the energy that is going out, okay, is so let's try to understand what is the energy that is going out. So the energy that is going out is nothing but the conduction flux that is going on as a convection flux to the fluid. Okay, but since we are considering the control volume such that the energy that is going out from the control volume is essentially going out to the fluid itself, because as I said, interfaces, if there is no phase change, interface cannot store energy. This means the energy that is coming out, or you can say the energy that is being generated inside this slab, has to be dissipated to the fluid, because there is no phase change taking place on the interfaces of the fluid solid, taking place at the fluid solid interface, which means, again I repeat, whatever the energy that is being generated inside this slab, all of these will be dissipated to the fluid, which means I can say that this this E dot out is nothing but H times the area of the slab, which is, so this is the area perpendicular to the direction of heat transfer, times the temperature difference, which is going to be the temperature at x equal to L minus T infinity. That's it. Okay, so you can appreciate that this is known, the volume is known because all the dimensions are given. Okay, the area of the slab is known, and all these things are known because you already know the temperature difference. Sorry, the temperature profile. Okay, so from this you can calculate the unknown H, that is this bit. Okay, so it's just the two lines that we have done, and you can appreciate the beauty of this method. Okay, it's just the two-line calculation that we have done, and if you are a master of it, you can just write this from in just one go if you understand energy balance and how to apply energy balance inside control volumes. Okay, so then your H is just going to be your Q double prime times your volume is going to be your area times twice L, because now your length becomes equal to 2 times the entire length, 2 times the length from x equal to 0 to x equal to L. So that's why this becomes twice L, because that is typically what the volume of the slab would be, and divided by the area of the slab. So this area and this area is exactly same. So this is also the area of the slab times, T at x equal to L minus T infinity. Okay, so this basically get cancelled. So you can say that your H is just going to be Q double prime twice L by T at x equal to L minus T infinity. So if you just evaluate this, you can easily show that you will get the same answer of heat transfer, which is just 5 watt per meter square Kelvin. So you can see that the entire math that we did all these things that we did by finding out K, then by finding out this then going on to find out this heat transfer coefficient. This can be very easily simplified if you learn how to use energy balance inside these kind of control volumes, and then finding out H. So once you know H, you can now say that your H times delta T is going to be your K into dt by dx, and then from here you can also evaluate what is the thermal conductivity of the slab. So it's kind of a reverse process that we are doing. We are first finding out H, and then we are finding out K by this. So we saw that from the energy balance, just by bypassing the heat diffusion equation, we can also calculate H and K in this manner. But the true spirit is that the heat diffusion equation comes from energy balance itself. It's like we are doing an integral. So what we are doing here is that we are kind of doing an integral approach here. Okay, and here what we are doing is we are kind of doing a differential approach here. Okay, it's just that the same thing. It's just kind of a two sides of a coin. It's just the same thing itself. It's just two phases that we are doing, in order to get the same answer that we just saw here. Okay, one is a differential approach, the second is just an integral approach to the problem. Okay, so this, I would say, this kind of problem. So very similar problem is there in your assignment too. I think that's the last problem. It's the same. So I guess it's not the same problem. I have made sure that it is not the same problem, because then it won't serve the purpose of you actually solving the problem. But the problem in your assignment, I would say, this is more simpler to the one that we just now solved here. Okay, so if you understand these problems, you can very easily solve the problems that are there in your assignment. And I hope that's the real part of learning that we seek to do in these kind of courses. Okay, we will never solve the problem that is there exactly in your assignment, because this is for you to do it. Okay, but at the same time, we will solve problems that are very similar. In fact, we'll solve problems that are a step that are one step higher to the problems that are there in the assignment, so that you guys will whenever you watch these videos and then you solve the assignment, these things will be easier for you, when you just solve the assignment on your own. Okay, but nevertheless, just feel free to ask us if there are any doubts at any point in whichever aspects you find your doubts arising. Okay, all right. So so this finishes the second problem, sorry, the third problem. And so as I said, this is one of the most important problems of I would say one of the most fundamental problems of conduction heat transfer, because it teaches us how to use the heat diffusion equation. It teaches us how to sketch temperature profiles. It also teaches us why the temperature profile is parabolic whenever there is a constant heat generation in a 1D system, and when your thermal conductivity is constant, all those assumptions. It also teaches us how to use boundary condition at the interfaces. Okay, so that's the reason why I feel this problem is it's a good problem, because it brings in all the associated concepts together. Okay, you also learn how to use the Fourier's law as well and things like that. After all, you also learn how to apply energy balance in controlled volumes as well in this problem. Okay, so we will stop here for today. We'll not solve any other problem. We have seen very nice three good problems on conduction. So at least now, I mean, at least up to this point, you should be comfortable enough to use Fourier's law. How to basically how to use Fourier's law to solve problems on conduction heat transfer, and basically you need to understand how you apply Fourier's law. You should be comfortable enough to solve to use the heat diffusion equation for Cartesian geometry at least, uh, to basically find out what the question seeks. Either you need to find out the temperature profile when everything else is given, or you need to find other properties when your temperature profile is given, as in this scenario. Okay, and you need to also be comfortable enough to apply boundary conditions at the interfaces. Okay, how do you apply boundary conditions at the interfaces is something that we have also learned this in through this problem. And please practice these kind of problems so that you can be familiar with these concepts. Okay, in the next class, what we will do is we will learn something which is known as conduction resistance. And as I said as I said in the first class, we will solve a very nice problem related to related to design of airplane windows, and we will use the concept of resistance network into the picture in the problem involving that heat transfer analysis of airplane windows. And we'll also see how heat transfer take place